in this context, what we should keep in mind is that, well, that when we find the inverse of this homotopic map, then that inverse is a manifold. We can't guarantee that if we find an inverse using this map, we do have a manifold, but that's exactly what we are trying to do. And that's why I introduced the third-term theorem before, because that theorem guarantees us that we can find a homotopic map, that this is possible. So that is why it's vital for the proof, because this step is very, very important. And, well, evaluating this map on a neighborhood of this kind of manifold gives us a tubular neighborhood of M. So I'm going to draw a picture. So suppose this is one of the planes of the Gaussian manifold, and we let this thing here be an image of our sphere near the Gaussian manifold. Now we had our tubular neighborhood. And the boundary. The boundary. The universal boundary. Well, it's once we've made this manifold so that the map is transverse, then we can stretch it to infinity and get our map correct. So, with a little bit more detail on maps and covering maps and so on, we do get that with these conditions we do get an injective map. And the fourth step is, well, it's more or less the same procedure. We need to show that it is injective, and to do this, well, we need that thing over there. We need that the manifold M, well, that we need some manifold to belong to the kernel of the map. So that is in detail. We also have our compactness condition on the N plus R sphere N, and again the same maps that we had before. We also have seen this from before, and we have some very, very similar way of proving injectivity, imposing some conditions onto the map, so that it homotopes to a transverse map. And well, those two conditions imply that the inverse image of the Gaussian manifold is in fact a manifold, and also some conditions on the boundary, and so on. But the key idea is perhaps, apart from transversality that I already mentioned, the key idea is that we have the manifold, we have the embedding in the Gaussian manifold, and our universal map, and we had a normal bundle we had identified with this tubular neighborhood over M. But the thing is that we don't want this map to be only just defined on this. We want it to be defined on the whole of the sphere. But well, this definition of the map is quite complicated, because in any way you risk adding points here, and you don't want that. You want to keep your Grassmann manifold here. So what Tom did, and that's why the theorem is that well, he added a point of infinity to the universal bundle, and then he mapped the tubular neighborhood to the universal bundle, but then he mapped the rest of the sphere is mapped to the point of infinity that he is adding here. So that's sort of the key idea in the proof of the Tom-Cobordism theorem, that the added point of infinity is what you use to map the rest of the sphere, and then you have a completely well-defined map. So now we have proved the theorem, and we're finished. Thank you.
What was the map L?
Ooh, the map L. This is probably not very well explained on the slides, because, well, to tell the truth, I had written quite a detailed proof of this thing, and it's a bit complicated. I'll load it on. I'll give it to Patrick so that he can load it on the web page alongside with the slides.
This question is perhaps connected to another one. What is so you get a map from the Tom space of the normal bundle to the Tom space of the canonical bundle of a DOR. But what is the map to the Tom space? You have a map from that to TBR.
You have a map?
This map. So you had a map from TBOR to TBR.
Yes.
What is this map? So at the end you get you got a map from the sphere to TBR.
Yes.
By going from the normal bundle.
Let's see if I locate.
A couple of slides.
You tell me.
Beginning of the proof.
It can't be very far away.
No, can't. Okay, forward.
Forward, I'm quite lost.
Yes, what is
Oh,
this
you
map
see,
from space?
you mean that I've cheated a little bit because I'm not putting TBR there.
Well,
that's cheating.
no,
I admit that it's cheating. There's a bit missing, and it's a very complicated bit with lots of maps. Well, you only just have to follow some maps, but well, to tell the truth, that's for an oriented cobordism, only just, and that makes things quite easier. Well, it's only just going through some more maps, but I'm not sure if that's what you're asking.
no, this is also true, but now I know what I meant. So you have in the middle, you have the map from Tom space
Here.
of the normal bundle, yes, to the Tom space of
Here.
gamma Rn.
Yes.
What is it?
Well, let's see, because if you have your M is embedded in the Grassmann manifold, I think we have it. No. Well, anyway, I explain. You have your M embedded in the Grassmann manifold, and then over the Grassmann manifold you have your universal bundle, and then as it's a universal bundle, you can pull back that you can pull back the normal bundle of M from that. So it's almost what we have on the board, and it just what I have written here. This way. So this map is clear. I mean, you have an embedding of M into the Grassmann manifold, and you have your universal bundle over the Grassmann manifold. So, as it is the universal bundle, you can pull back the normal bundle of M, that is over M. So this is just a pullback construction. Is it okay? So, and then it's just what we were saying before during the break, that that you have this map, and that you can consider just the Thom spaces of this bundle and this bundle. It's almost the same map, and it's just that you are considering Thom spaces. And that's the map that you have over there, over here. So that should be well. Is it okay? And then the next is just the inclusions that we saw before, and then we arrive to our famous notation.